lens of physics. Newton's first law of motion, also known as the law of inertia, can be stated quite simply. An object at rest will stay at rest, and an object in motion will stay in motion at a constant speed and in a straight line unless acted upon by an external force. This fundamental principle is the cornerstone of classical mechanics and helps us understand the behavior of objects in our everyday lives. In other words, objects are naturally lazy. They prefer to keep doing whatever they're already doing, whether that's staying still or moving in a straight line. They resist changes to their state of motion. This resistance is what we call inertia, and it's a property inherent to all objects with mass.
Think about a book resting on a table. It will happily remain there indefinitely unless someone or something comes along and applies a force to move it. When you push the book, you're applying an external force that overcomes its inertia, causing it to move. Once the force is removed, the book will eventually come to a stop due to friction, another external force acting upon it. This is inertia in action.
Now, imagine you're riding in a car that suddenly slams on its brakes. Your body instinctively lurches forward because it wants to continue moving at the same speed the car was traveling before braking. This happens because your body has inertia, and it resists the sudden change in motion caused by the braking car.
Seatbelts are crucial in this scenario because they provide that external force needed to counteract your body's inertia, preventing you from continuing forward into the dashboard. Without a seatbelt, your body would continue moving forward at the car's previous speed, leading to potential injury. Inertia is the reason we wear seatbelts, and it's a powerful reminder that objects in motion tend to stay in motion. This simple yet profound law of physics governs much of the movement we observe in the world around us, making it an essential concept to grasp. Newton's second law of motion takes us beyond the concept of inertia and introduces the relationship between force, mass, and acceleration. This fundamental principle is a cornerstone of classical mechanics and helps us understand how objects move and interact in our world. This law is neatly summarized in the famous equation F equals ma, where F stands for force, m for mass, and aa for acceleration. This equation is not just a formula. It is a powerful tool that allows us to predict the behavior of objects under various forces. In simpler terms, the acceleration of an object is directly proportional to the net force acting upon it and inversely proportional to its mass. This means that if you apply more force to an object, it will accelerate more, but if the object has more mass, it will accelerate less for the same amount of force.
Let's unpack that a bit. Understanding this relationship can help us in everyday situations and in complex scientific calculations. Imagine pushing a shopping cart with a certain amount of force. The cart will accelerate or speed up in the direction you're pushing. The lighter the cart, the easier it is to push and the faster it will go. Now imagine pushing a car with the same amount of force. The car, being much heavier, having more mass, will accelerate much more slowly than the shopping cart. This is a clear demonstration of how mass affects acceleration.
This is because the car's greater mass requires a greater force to achieve the same acceleration as the lighter shopping cart. The more massive an object, the more force you need to change its motion. Newton's second law helps us understand why it's easier to push a small, empty shopping cart than a large, fully loaded one. The difference in mass between the two carts means that the same amount of force will result in different accelerations. This principle is not only crucial in physics, but also in engineering, automotive design, and many other fields.
Newton's third law of motion is perhaps the most well-known, even if people don't realize it's a scientific principle. It's a fundamental concept that governs much of our everyday experiences. It states, "For every action, there is an equal and opposite reaction." This simple yet profound statement encapsulates a universal truth about the nature of forces. This means that forces always come in pairs. Whenever you push or pull something, there's always a counterforce pushing or pulling back. Whenever one object exerts a force on a second object, the second object simultaneously exerts an equal force back on the first object, but in the opposite direction. This interaction is constant and unyielding.
Think about jumping on a trampoline. It's a perfect example of Newton's third law in action. You exert a downward force on the trampoline surface, the action. The surface compresses under your weight. In response, the trampoline exerts an equal force upward on you, the reaction, propelling you into the air. This back and forth motion is a direct result of the forces at play.
This action-reaction principle is also why rockets launch into space. It's a spectacular demonstration of Newton's third law on a grand scale. The rocket expels hot gas out of its engines, the action, and the gas, in turn, exerts an equal and opposite force on the rocket, the reaction, propelling it upward. This continuous expulsion of gas allows the rocket to overcome Earth's gravity and soar into the cosmos.
While we've explored Newton's laws individually, it's important to remember that they don't exist in isolation. They work together, like instruments in an orchestra, to create the symphony of motion we observe in the universe.
Consider a simple act of walking. As you push your foot against the ground pushes back with an equal and opposite force, propelling you forward. Your body's inertia would keep you moving at a constant speed in a straight line, if not for friction and air resistance, which act as external forces. Finally, the acceleration you achieve while walking is determined by the force you exert on the ground and your body mass.
This simple act of walking demonstrates the elegant interplay of all three of Newton's laws in action.
Newton's laws are not just confined to textbooks or physics classrooms. They are constantly at play in our everyday lives.
When you drive a car, the engine generates a force that turns the wheels. The friction between the tires and the road provides the necessary force to accelerate the car forward. When you jump up, the force you exert downward on the ground is met with an equal and opposite force that propels you upward. Even the simple act of sitting still is governed by Newton's laws. The downward force of gravity on your body is balanced by the upward force of the chair, keeping you at rest.
The world of sports provides a captivating arena to witness Newton's laws in action. In baseball, a pitcher uses force to accelerate a baseball towards home plate. When a batter hits the ball, the force of the bat causes the ball to change direction and accelerate.
In basketball, when a player jumps for a slam dunk, they are using the force of their legs to overcome their inertia and propel themselves upward. Even the graceful movements of figure skaters can be explained by Newton's laws, as they use their edges to push against the ice, generating forces that allow them to glide, spin, and jump. Section 8, Beyond the Basics, Newton's Laws and Advanced Technology.
Newton's laws are not only fundamental to our understanding of the world around us, but also form the bedrock upon which countless technological advancements have been built. Engineers rely on these laws to design everything from cars and airplanes to bridges and skyscrapers. Understanding the forces at play is crucial for ensuring the structural integrity and safety of these structures.
Rocket scientists use Newton's laws to calculate the precise amount of thrust needed to overcome Earth's gravity and launch rockets and satellites into space. Even the development of sophisticated technologies like robots and self-driving cars relies heavily on Newton's laws to control motion and navigate complex environments. Section 9. The Enduring Legacy of Newton's Laws, a Foundation of Understanding.
Sir Isaac Newton's laws of motion have stood the test of time, remaining as relevant and insightful today as they were centuries ago. They are not just a set of rules, but a profound framework for understanding the universe. They have enabled us to comprehend the motion of planets and stars, design groundbreaking technologies, and even send humans into space.
The elegance and simplicity of Newton's laws lie in their ability to explain a vast range of phenomena, from the mundane to the extraordinary. They serve as a testament to the power of scientific inquiry and the human capacity to unravel the mysteries of the natural world. Section 10. Conclusion. Reflecting on the elegance of motion. As we've explored, Newton's laws of motion are far more than abstract principles confined to textbooks. They are the very rules by which our universe operates, shaping the motion of everything around us, from the simplest actions like walking or throwing a ball to the most complex engineering feats like launching rockets or building skyscrapers. Newton's laws are constantly at play. By understanding these laws, we gain a deeper appreciation for the elegance and predictability of the physical world. We begin to see the forces at work in every interaction, and we develop a greater sense of awe for the interconnectedness of our universe. At Section 11, Challenge Yourself. Become an everyday physicist. Now that you've delved into the fascinating world of Newton's laws, I challenge you to become an everyday physicist. Observe the world around you with a newfound awareness. Notice how objects move, how forces interact, and how these fundamental laws govern even the most ordinary events. You'll be amazed by the hidden beauty and elegance of physics that you'll discover in the everyday.